voltage from 3.3 volts to 5 volts. The reverse operation is possible. The clock signal CPV of the shift register is transformed by the level shifter into CKV. It is the same clock signal but with a higher digital voltage value. CKV is an abbreviation for vertical clock, the clock that controls the vertical scan. The level shifter chip can be integrated into the gate drive chip, or integrated into the TCON microprocessor. It can also be found as a separate chip on the TCON board. To locate it on the TCON board, look for markings such as CPV, CKV, STV or VST, which mean the same thing. Here is an example of a level shifter chip on this TCON board. At the input of the chip you will find the terms STV and CPV. There is also the term OE. At the output of the level shifter, the conductive tracks are engraved on the back of the board and then reappear at the test points, which are directed to the connector of the screen. We can see the term CKV, but there are also other terms such as CKVB and STVP. Note that on this board the VGH and VGL are labeled V on and V off respectively. The level shifter transforms CPV into CKV. The STV signal is transformed into STVP. CKV and STVP are the same signals as CPV and STV respectively, but CKV and STVP have a higher voltage value. From this level shifter will come another clock signal, which is the CKVB. This signal is the inverse of CKV. It is also used to control the gate of TFT transistors. The B that has been added to CKV comes from the word bar because the inverse of a value is mathematically noted by a bar above the letter that represents it. Here is a chronogram that represents the correspondence between CPV or CKV and the output signal of the gate driver. At the rising edge of the first clock pulse, the first output of the gate driver called G1 is activated. Note that the activation time of a line is equal to the duration of a clock pulse, which includes a high clock level and a low clock level. At the second pulse of the clock, still on its rising edge, the second output of the gate driver G2 is activated while the previous output G1 is stopped. The same process will take place successively until all the gate driver outputs are scanned. The disadvantage of this process is that there is a certain waiting time between the activation of each output. To shorten the scanning time of all the lines, we added another clock signal with a period inverted with respect to CKV, called CKVB. The principle of operation is as follows. Instead of waiting for a new signal from CKV, the second output G2 is connected to the CKVB signal. Thus, the two clocks work at the same time but with a shift between the rising edge of each of the clocks. With this organization, CKV will drive the odd lines while CKVB will drive the even lines, thus saving time to scan all the outputs of the gate driver. When there are several gate driver chips, for example 3 chips that control each 360 outputs in horizontal lines, we assign to each gate driver a pair of CKV and CKVB signals and we add a number 1, 2, 3, to identify them. Each clock will control 180 lines. CKV1, 2 and 3 be assigned to the odd lines. CKVB1, 2 and 3 will be assigned to the even lines. We find the terms CKV1, CKV2, CKVB1, CKVB2 in Samsung panels, but other companies use other terminology to designate the various clock signals. In LG panels, the terminology used is CLK1, CLK2, VGH odd, VGH even. In the AUO panel is used HC1, HC2, LC1, LC2. HC is an abbreviation of high clock and LC low clock. The level shifter can be located both before and inside the gate driver. Here it will allow to transform the digital signal VDD and VSS into VGH and VGL. If the output of the logic circuit is at a high level or 1, it is translated to VGH. If the output is at a low level or 0, it is translated into VGL. The last step in the gate driver, before the VGH and VGL voltages reach the TFT transistors, is their passage through a buffer. The latter is a voltage follower circuit whose purpose is to separate the circuits present in the gate driver from the TFT transistors and storage capacities that are inside the panel and constitute the load to be supplied with voltage. We now arrive at the OE signal, which is a contraction of the words output enable. We see that this signal is placed downstream of the output of the shift registers. The role of the OE signal is to control the activation time of each output. Here is the reason. In this illustration, in green is represented the voltage VGH, which feeds the gate of transistors placed on the same line. This conductive line is not perfect because of the parasitic effects, which are the resistance of the conductor and the presence of a parasitic capacitor between gate and source called here CGS. The resistor and the parasitic capacitor constitute an equivalent of RC circuit low-pass filter. The electrical pulse VGH that we call gate pulse must travel a certain length from left to right. With the parasitic effects of conduction, the VGH signal will undergo a distortion on its rising and falling edge. We see the signal at the beginning of a line is not exactly the same at the end of the line. This distortion can be seen especially with large screens for an obvious reason of the longer line to cover. This defect of conduction has consequences on the quality of the display. On this diagram is represented the progression of the display of the image line after line. At the time of the activation of the first line, the data of the image is delivered to the corresponding line and with the adequate time. Then it is the turn of the second line to be activated with VGH while the previous line is switched off with VGL. The coordination process between the lines and the data will continue successively until all the lines are scanned. It is the T-Con board that ensures the coordination between the activation of a line and the delivery of the data to the corresponding line. As a reminder, T-Con is an abbreviation of timing control.